So I will tell you a bit about proof complexity. So I kind of I looked at the chat. So I've seen that there are people really with different backgrounds, mathematics, computer science, and also at a different stage of their studies. So I will try to do it. I mean, to really define everything. But of course, if there are any questions, if there is any notion that you want me to explain, and then please ask. Yeah, so I will be talking about proof complexity. So let us have a look at the slide. So we can consider some property of structures. So let's say that we are interested in the question whether a graph is three-colorable. So by three-colorability, I mean whether there exists an assignment of 3 different colors to the vertices of the graph, such that whenever you have 2 vertices that are adjacent, they get different colors. So this is some well-known property of graphs that complexity has been studied. So we can ask different questions about this property. So the classical question that I mean we all know about is we can ask about the decidability procedure. So how complex it is to decide whether a graph is three-colorable. So here we can think about different computational models like Turing machines, but also circuits, and then different complexity measures like time complexity or space complexity or the size of the circuit that decides this property. So this is the kind of questions that I mean, at least if you are studying computer science, then of course you are familiar with. Then, since this is a logic workshop, then you are probably also familiar with the question, how complex is the language that describes this property? So, I mean, here by a language, I mean a logic. So, for instance, it's kind of not very difficult to see that in first order logic, we cannot describe this three-colorability and then like second order logic is enough, but I mean, we can ask about different logics, whether this property is expressible in this logic. And then there's the question that I want to focus on today. So how complex is the proof of the property? So whether if I want to prove to you that the graph is three-colorable, then what does it take? So let us have a look at this slide again a bit with more details. So, I mean, of course, the first question is, I mean, this is the question that we consider if we are talking about computational complexity. Then the second question is what we are looking at when we are looking at logic, or more precisely, descriptive complexity or finite model theory. And as I said, I want to focus on this third question and explain to you a bit, give you more details about this question, which is a subject of proof complexity. And also, I put some arrows on this slide. So of course, there are connections between those 3 different sub-areas of theoretical computer science. And so, except for telling you a little bit about proof complexity, I also want to mention some connections between proof complexity and logic on one hand, and proof complexity and computational complexity on the other hand. Okay, so yeah, so maybe just to give you a little bit of an outline. So first I will kind of give you an introduction about what proof complexity is about. I mentioned some complexity measures that we study in computational complexity, like time or space. So I will also give you examples of proof systems and different complexity measures that we consider in when we are talking about those proof systems. And finally, I will talk a little bit about some connections between proof complexity and well, mostly logic. Okay, so let me start with some basic definitions, just so that we are all on the same page. So I will be talking about proof systems for propositional formulas. So I mean, in our first slide, I mentioned that we want to know how difficult it is to prove that a graph is three-colorable. So I mean, propositional formula can actually encode, I mean, a lot of properties like this. So in particular, we can encode the three-colorability as a propositional formula. So we basically, if we are talking about proof complexity of certain properties, like properties of structures, then what we do is we encode them as propositional formulas and then try to prove those propositional formulas. So in a propositional formula, we have variables. I will denote like this bar over a variable. And then we have connectives, disjunction and conjunction. A variable or a negated variable is called, I will call them literals. And then, well, a clause is just a disjunction of literals. And then often I will be talking not about arbitrary propositional formulas, but about propositional formulas which are in conjunctive normal form. So this one here is in a conjunctive normal form. So it's a conjunction of disjunctions or conjunction of clauses, in other words. Okay, so that's just a few basic definitions. So now, well, let's just have a look. This will be important for one thing that I will mention later. So if we have all propositional formulas, then of course we can, they are either satisfiable, and we know that the satisfiability problem is NP-complete. So this means that, and then the complement are those which are unsatisfiable. So this means since sat is NP-complete, then the problem of the unsatisfiability problem is co-NP-complete. Yeah. So kind of for at least for this talk, I will be talking about proof systems for unsatisfiability. So we will be proving that a formula is not satisfiable, so that there does not exist a 0-1 assignment, which makes the formula, the propositional formula, true. And the proof system for the set of unsatisfiable Boolean formulas, here we have, so this is a definition due to Cook and Recco in 79. So here you have an informal description. So let's say that you give me a propositional formula X, and I claim that it's unsatisfiable, and I give you a candidate proof pi for the fact that the formula is unsatisfiable. And the crucial property of a proof system is that once I give you this candidate proof, you can check in time polynomial in the size of the formula and the proof that I gave you, that indeed pi certifies that X is unsatisfiable. So this is an informal description. Here you have a more formal definition. So a proof system for the set of unsatisfiable formulas, here we are considering it as 0-1 strings. So of course, I mean, well, we want to see them as input for Turing machines. So we encode them in some way as 0-1 string and as 0-1 strings. So it's a predicate, or you can think about it as a Turing machine. It's decidable in polynomial time, and then it has two properties. So whenever some pair of strings, so this is a pair of a candidate proof and an encoding of a propositional formula, whenever this machine accepts this pair of strings, then this means that indeed X is unsatisfiable. So whenever we have a proof, then X is unsatisfiable. And also we have completeness. So for every unsatisfiable formula, for every string that encodes an unsatisfiable formula, then there exists some pi, some proof, which such that pi X is accepted. So such that pi is indeed a proof of unsatisfiability of X. Yeah, so this is a formal definition of an abstract proof system. And now in the rest of my talk, I will define concrete proof systems, and yeah, we will be talking about some properties of concrete proof systems. And also one piece of terminology. So a proof of unsatisfiability is often called a refutation. So I will be talking about, sometimes I will be talking about proofs, but sometimes I will be just talking about refutation. So basically I will use this those two things interchangeably. Okay, so let us have a look at an example of a proof system, which is kind of a trivial proof system. So an example of a proof system is a truth table. So let's say that you give me a propositional formula. So here we have also implication, but of course implication can be encoded using the other Boolean connectives. So let's say that you give me a propositional formula like this, and the proof that it's unsatisfiable that I return to you is just this, I mean, of course, an encoding of this table. So I just give you, for every truth assignment to P and Q, I tell you that's indeed, like if you assign 0 to P and 0 to Q, then indeed this formula will be unsatisfiable, and so on. So I'll just give you the, like, I mean, I just give you the value of the proof of the truth value of the formula for any possible assignment to the variables. So that's a good proof system. So it satisfies the requirements. If I give you such a table, you can check in polynomial time whether indeed I'm telling you the truth. The problem with this proof system is that whatever you give me, the proof that I return to you is of exponential size in the size of the formula. So this is something that we want to avoid. So here is another important definition. So we would be most happy to have something which is called polynomially bounded proof system. So a proof system is polynomially bounded if for any unsatisfiable formula, there is a proof whose size is at most polynomial in the size of the formula. So the problem with this very nice requirement is that it's not very realistic. So I mean, this is related to the fact that unsat, as we've seen, is co-NP complete. So Cook and Recco observed basically that a polynomially bounded proof system for unsatisfiable propositional formulas exists if and only if NP is equal co-NP, which is something that we don't expect to hold. So basically, proof complexity is about studying different proof systems and kind of hoping that they are strong enough, but also hoping to prove that eventually there is no proof system can be polynomially bounded. So this is something that is called sometimes Cook and Recco program. So basically, they proposed to approach the question of NP not equal co-NP by showing that there is no polynomially bounded proof system for unsatisfiable propositional formulas. So this is kind of, let me talk a little bit about motivations for studying proof complexity. So this was kind of an original motivation. So I would say that now I don't think anybody realistically hopes that from studying different proof systems, by studying different proof systems, we will actually be able to show that NP is not equal to NP. So just one thing, so this would also imply that P is not equal to NP. So that would be like a really big thing. So I don't think that anybody realistically hopes to do this, but I mean, this is, let's say, one of the motivations. Another motivation is to rule out large families of p-time algorithms for problems in NP. So basically, very often, our proof systems would correspond to some algorithms, which could be efficient algorithms. So by showing lower bounds, by showing propositional formulas which do not have small proofs in a certain proof system, you can rule out some algorithms which you could potentially hope that could solve those problems. On the other hand, we also could, so for some, let's say that for some class of propositional formulas, you manage to prove that in some proof system you have small proofs, then this kind of results you can translate into efficient algorithms for certain problems. So yeah, so you have those two kind of sides. I mean, both lower bounds and upper bounds tell us something. And then there are some more practical motivations. So those are motivations connected to the, related to the connection between proof complexity and SAT solvers. So SAT solvers are based on proof systems, mostly on one proof system that I will focus on during most of my talk, called resolution. So by analyzing resolution, we can prove upper and lower bounds for proof systems. Of course, there is also like SAT solvers usually do a bit more or use different heuristics, which we kind of do not capture, but by our basic definitions of proof systems. So then we can try to formalize also those heuristics that SAT solvers are using to be able to tell actually more about what happens in practice. And well, yeah, exactly. So we want to try to explain and predict what happens in practice. And also somehow, like, I mean, there are also hopes that some other proof systems in resolution that we are considering could also influence the SAT solving industry. This has not happened so far, I think, but there is also this possibility. Yeah, so that's it. That's it for motivations and kind of basic framework. So now let me show you a bit. So I mean, that's a picture. So here you have some proof systems. I would say that perhaps those are the most studied proof systems, but I mean, I'm sure that there will be people who disagree with me. So that's let's say a zoo of different proof systems that are being studied, and this is by far not a complete picture. Yeah, so there are many arrows on this picture. So this is something. So this is something that is also an important question. So when you are considering two different proof systems, you want to compare their strength. So here in this this picture, you have arrows like this, kind of normal arrows, well, here and here. So by this arrow, I mean that if you give me a proof in the resolution proof system, then there exists a polynomial time procedure which will translate this proof into a proof in the cutting planes proof system. So that means that basically cutting planes, so we call it a polynomial simulation. So this basically means that if you have a proof in resolution, then you have also a proof in cutting planes, which is not bigger. I mean, at most polynomially bigger, but so cutting planes is in some sense at least as strong as resolution. And also this solid arrow means that there exists an unsatisfiable propositional formula which has a small proof in cutting planes and requires big proof in resolution. So this is, so basically this kind of arrow means that the proof system here, this proof system is actually stronger than this proof system. Then there are things like this here and here, those dashed lines. So this means that those proof systems are incomparable. There are formulas which have small proofs here, big proofs there, and so on. This means, this dashed arrow means that there is a formula which requires a big proof here and small proof here, and has a small proof here. So maybe this system is stronger, but we don't have this polynomial simulation. And then there is, I think there is one more type of arrow here. So between Frege and extended Frege. So this means that in extended Frege, I mean, that extended Frege simulates Frege. So whenever you have a small size proof in Frege, then you can translate it into a proof in extended Frege. But we don't know about a formula which would require big proofs in Frege and have a small proof in extended Frege. Actually, we don't have any lower bounds for those two proof systems. As far as, I mean, we could, it can be that those proof systems are actually polynomially bounded. Yeah, so this is kind of to show you that, I mean, there is, so I will define it to you I mean, at most 3 proof systems. We'll see how much time we have, but this is to show you that, I mean, there are really a lot of them being studied, and one important question that we are looking at is how do they compare? Like, yeah, I mean, comparing their strength is one important thing that we are thinking about in proof complexity. And yeah, so one more thing maybe on this slide is that basically here there is a cut. So we know that all the proof systems which are below this line, we know that they are not polynomially bounded. So we know about formulas, unsatisfiable propositional formulas, which require proofs of exponential size. And for extended Frege and for Frege, we don't know. So yeah, perhaps those proof systems are polynomially bounded. Probably not, but it's still, I mean, it hasn't been refuted, this this statement. Okay, so yeah, so as I said, I want to now give you some concrete, I mean, tell you a bit about some concrete proof systems. So I will tell you about resolution. I will hopefully also tell you about polynomial calculus and sum of squares proof systems. Yeah, so before we start this part, let me just give you this lemma. So it's not very difficult to prove that any Boolean formula, any propositional formula, can be efficiently translated into one which is a CNF. This is a translation which preserves unsatisfiability. So if f is unsatisfiable, if and only if f prime is unsatisfiable. So just a reminder, a CNF is a conjunction of clauses. So here you have an example. So this means that basically, if we are interested in those polynomially bounded proof systems and so on, we can just focus on proof systems for CNFs, and this is what I'm going to do. So now, instead of talking about proof systems for arbitrary unsatisfiable propositional formulas, we are going to be talking about proof systems for unsatisfiable CNFs. So resolution, it's definitely the most well-studied proof system. Originally described by Blake in 1937, and then in the context of proof complexity and SAT solving, etc., it was studied by Davis and Putnam in the 1960s. And as I already mentioned, it's a basis of modern SAT solvers. It has one rule. So as I said, now we are going to focus on CNFs. So conjunctions of clauses. So when we have two clauses, B is also a disjunction of literals, and C is also a disjunction of literals. So if we derive those two things, where here we have X and here we have not X, then we can get rid of the X altogether and just derive from those two B or C. So let's have a look at a concrete example. So this is just the one rule that we have in this proof system. So let's say that we want to prove that this CNF on top here is unsatisfiable. So first of all, instead of looking at it as this formula, we look at it as set of clauses. So we just look at it as set of those clauses. And the thing that we want to show is that they are not. There is no assignment, 0-1 assignment, which would satisfy each of them, right? So here we have, again, all of those clauses as a set. And now in resolution, we will just derive new clauses from those which we already have. So we start with the ones which appear in our CNF, and then derive new clauses from this. So meaning that whatever we derive, this means that it follows from the previous clauses. So whatever truth assignment would satisfy the previous ones, it will satisfy the one that we derive. And we do it using the resolution rule. So here, let's say we apply the resolution rule, let's say here, to those two clauses. So we have not X or Z, and we have not X or not Z. And well, we can, as I said, we can get rid of Z and just derive. So this will be not X or not X. So of course we can just simplify it to just not X. And and I mean, here again, we have those two clauses. So here in this clause, we have Z. In this clause we have not Z. So from those two, we can derive a disjunction of this and this, which will be X or not Y. So I hope it's clear that if we have an assignment, truth assignment, which would satisfy those two clauses, then it will necessarily satisfy this. So this is indeed a derivation rule. And resolution refutation looks like this. So we just apply, I mean, like this example. So we just apply the resolution rule until we get, eventually we get, I mean, hopefully if we manage to prove that it's manage to complete the proof of unsatisfiability, we will arrive at clause X and not X. And then when we resolve it, we get an empty clause, and this is contradiction. So basically, in other words, if you want to see it differently, like if from our original clauses, we can derive that it's X and not X, then this is clearly a contradiction. This cannot both hold, right? So we get an empty clause which is not satisfied by any assignment. And it's not very difficult to show that indeed CNF F is unsatisfiable if and only if there is a derivation like this of an empty clause. So here on this picture, this proof is a tree, but in general it can be a directed acyclic graph. So you can reuse things. So right, I mean, you could also reuse this stuff again, right? If you derive something, then you can use it many times to derive new things. So that's a definition of resolution proof. And now I told you that I want to mention some complexity measures that we are interested in when we are talking about proofs. So the most important one is the size, or in when we are talking about resolution, we also sometimes call it length of a proof. So in the case of resolution, we often define it as a number of clauses in the proof. So in this case, the size would be 9. So this is because, I mean, the size is the size as kind of as introduced in the first definition. So it's just that clauses are small. They have, like, if we have n variables, then the clause is at most of size n. So this is polynomially related to the size. If we would just encode it as a 0-1 string, this kind of proof, then I mean the size of this string would be kind of related to the number of clauses in the proof. So so this is the definition of this is the basic complexity measure for resolution proofs. And now I want to give you, I mean, I want to show you, not really show you, but to give you the first theorem, first lower bound that we got in proof complexity. So this is a lower bound for pigeonhole principle for the size of resolution proofs. So a pigeonhole principle says that if we have m and n, where m is greater than n, then m pigeons cannot fit into n holes without sharing holes. So now, as I said, when we are talking about proof complexity of statements like this, we encode them as propositional formulas. So here, how do we encode this statement as a propositional formula? We choose one variable for every pair pigeon and hole. So this is just a Boolean variable, Pij, and the meaning is that if it's false, then, I mean, if we assign 0 to it, then pigeon I does not go to hole j, and if it's true, then it does. And we write a formula which we want to be unsatisfiable. So we write a formula which means that actually there exists such an assignment of pigeon to holes, such that they do not share a hole. So any pigeon gets to one hole. This is this junction, and no hole gets to different pigeons. So this is what is written here, I hope. Yeah. Yeah, so this is an unsatisfiable formula because we know that it's impossible to fit m pigeons into n holes. And Haken in 85, so this is basically also sometimes considered as the first modern kind of proof complexity theorem. So Haken showed that if you have n+1 pigeons and n holes, and you write and you have this class of Boolean formulas, then refuting this in resolution requires a length which is exponential in the number of variable, actually in the number of pigeons, but also in the number of variables here. Yeah, so I'm not gonna give you the proof of this theorem, but I mean, this is basically the only lower bound that I will give you in this talk. So and this is the kind of first one that we had. So let me just briefly, I think I really, of course I have too much material for this short talk, but let me just briefly mention to you some other complexity measure for proofs for resolution. So we can also consider the width. So this will be the size of the biggest clause in refutation. So here I have some comments about it, but maybe let's skip them. So another thing I kind of mentioned to you, I think also that one thing that we are interested in proof complexity is also the relationship between different complexity measures. So this is a very important and influential theorem by Benson and Wilgerson. They proved this kind of trade-off between resolution width and resolution size. So, I mean, this is a complicated formula that is in the statement of the theorem, but basically the corollary is that if you manage to prove a linear lower bound on width, so if you manage to prove that whenever you have a resolution refutation of some formula, then there will be clauses in this I mean, if you want to, yeah, there will be clauses in this refutation which are big. They have linear number of variables. Then this implies then that whenever you have a resolution refutation, then this refutation has to have an exponential size. So this way you can get lower bounds for size from lower bounds for width, which are often easier to show. Yeah, so let's say that let's finish for resolution. And now I want to give you an example of another proof system, which is very different. So let me just finish this quickly, and let's move to something else. So now I want to give you an example of a proof system which talks about CNFs, but not directly. So consider this this clause here. So resolution can be seen as a proof system for refuting sets of clauses. So now we will be looking at a proof system for refuting sets of polynomial equations. So how come? I mean, why? Since we want to refute CNFs, why can we talk about refuting sets of polynomials? Well, if we have a clause like this, then we can encode it as a polynomial equation here, and it's not very difficult to see that they have exactly the same satisfying 0-1 assignment. So in this case, it will be like any assignment is satisfying except for the one which assigns 0 to x, 1 to y, and 0 to z. So this means that if we start with a set of clauses, then from this set of clauses, using this kind of translation, we can get set of polynomials. And instead of showing that there is no satisfying assignment, no assignment which would satisfy all those clauses, we can try to show that there is no assignment which will satisfy all those polynomial equations. 0-1 assignment in both cases. So one proof system which does this, so there are different proof systems for polynomial equations that are being studied, and one of them is polynomial calculus. So as I said, it's a proof system for showing that polynomial equations have no common 0-1 solution. And here are the rules of this system. So when we have two polynomial equations like this, then we can derive its sum. We can also, if we have a polynomial equation, then we can multiply it by some scalar. We can multiply it by some variable. And we can also, since we are interested in 0-1 solutions, we can also always use, I mean, for free, we can derive equations like this. So here you have a rather trivial polynomial refutation in polynomial calculus. So let's say that we start with those three polynomial equations. So our goal is to use those rules to derive, again, as in the case of resolution, to derive a contradiction. And then we conclude that the original system of equations does not have a common 0-1 solution. So here we have, so here the kind of contradiction that we get is 0 equals 1. And here, I mean, you can have a look at those arrows. So indeed, in each case, I mean, for instance, we start by taking this equation and multiplying it by -1, and we get this equation. So this is this derivation. This is applying this derivation rule. Then I guess we are just adding those two equations. So those two arrows mean that we are adding those two equations to get x equals 0, and so on. I mean, that's a very trivial example. But I mean, I just wanted to show you this to show you that, I mean, those proof systems that we are studying here, they can be really different in the sense that, I mean, some of them can operate on formulas, also like not necessarily CNFs, but some more complicated propositional formulas. But some are also, in some cases, we are just considering sets of polynomial equations, and they are very different. So as you can imagine, there are very different methods that are being used to study those different proof systems. So here we have like all this algebra that comes into the picture. So unfortunately, I will not. Yeah, okay. So and then of course there are also like complexity measures, which are in the end they turn out to be very related to the complexity measures that we consider for resolution. But I mean, in principle, they are different. So there is the size, and I mean, then the monomial size, which is just the number of different monomials which appear in the proof, and then there is a complexity measure which seem to be very different. So we can look at the maximal degree of the polynomial that appear in the proof. And similarly, there are theorems that relate those complexity measures to each other. Okay, so I wanted to show you one more proof system, but unfortunately, I'm afraid that I don't have time. So this will be in this proof system, you encode clauses as inequalities, and you do something with those inequalities. So what is interesting in this proof system, which is called sum of squares, is that in this case, instead of having a bunch of rules, so you can, the previous two proof systems, you could call them dynamic proof systems. So you have a bunch of rules and you derive, I mean, you derive a sequence or this graph. I mean, you derive new things. You hope to get a contradiction by deriving new things using those rules. And here, a proof is just a single identity like this. So this is sometimes called a static proof system, but unfortunately, I don't have time to get into details here. So yeah, so let me conclude by just telling you a little bit about connections. So as I said, I think that what is very nice in proof complexity is that it's somehow, I mean, not in between, but it has like strong connections both to this more like track A stuff like algorithms and complexity, and on the other hand, well, clearly to logic. So track B things. So yeah, so there are interesting connections between proof complexity and circuit complexity. Some proof systems manipulate circuits. Communication complexity. So I don't know if you know what it is, but I mean, some lower bounds in communication complexity can be translated to lower bounds in proof complexity. So I mentioned a bit, I talked a little bit about algorithms, and in particular optimization algorithms. I mean, something that I did not really talk about, but there is a whole research area called bounded arithmetic. So this is something which is very connected to mathematical logic, and there are interesting I mean, basically this is considered part of proof complexity, I would say, even sometimes, and there are interesting connection between proof complexity and this well, mathematical logic, and also proof theory. And there is also something that I'm particularly interested in. So connections between proof complexity and finite model theory and descriptive complexity. I have one slide to tell you a little bit about this, but I think that it's, yeah, I mean, I have so little time that I think it's going to be, I mean, it's going to be very brief. So let's say that you have a graph. So as I already mentioned before, you can write a propositional formula which says that this graph is tricolorable. And then if the graph is actually not tricolorable, you can think about refuting this in different proof systems. So this propositional formula can be encoded as a relational structure. And actually we can, without going through this propositional formula, we can just construct in logic from the graph immediately an encoding of a propositional formula which claims that it's tricolorable. And now if in descriptive complexity, we have a theorem which says that the property of the tricolorability is not expressible in some logic. So this would be a theorem. Let's say that you have such a theorem in descriptive complexity. Then it's enough to, I mean, it's enough. Sometimes it's hard actually. So if you then show that, for instance, having with K resolution refutation is a property which is expressible in this logic, then you can conclude from this kind of reasoning that the property G is tricolorable that does not have bounded resolution width. So there is no K, so that whenever a graph is not tricolorable, then you can refute it with resolution proofs of this width. So I mean, that's just a sketch, but this is kind of to argue that using theorems from descriptive complexity, we can lift. So this you can see it as a lower bound from descriptive complexity. You can translate this to a lower bound in proof complexity in this way. Okay, so that's it. I had to skip a bit, but thank you very much for your attention. Maybe just like a short. So this is a mentoring workshop. So maybe just one comment. So I finished my PhD 5 years ago. And actually, when I finished my PhD, I had I knew strictly nothing about proof complexity. So all I learned about proof complexity was during my postdoc. And I think this is something that I would, of course, if you plan to be a researcher, I think this is something that I would really encourage you to do. I mean, to be open to new areas. I mean, of course, I think could be slightly risky to start doing something completely different during your postdoc, because of course this is also the time when you want to finally, get some permanent job. But I mean, being open to areas which are connected but new, I think this can be really enriching and very interesting. And this is how it was